Okay, so we essentially finished the material, everything that we wanted to cover in this class, and this is just a practice review of several problems. Okay, first question, first problem. Can you become addicted to exercise? Franchise of workout facilities performed a study to answer that question. They took a sample of exercisers who usually work out every day, and after that they asked them, how do you feel on average? On the scale from 1 through 5. 1 being very tense and anxious, 2 being just tense and anxious but not very, 3 is okay, not too bad, 4 is actually relaxed and happy, and 5 is excellent. Okay, so that obviously is an ordinal data. After that, they told this group of people to stay out of exercise for the next 3 days. So break your typical routine, right, and see how you feel. And moreover, they were told to be as physically inactive as possible. So just sit in front of the computer, do nothing, okay, or watch TV. And then after that, after 3 days, they asked them to finish the same questionnaire. How do you feel on a scale from 1 through 5? And the answers are recorded in the file exercise. So let's open up the file exercise right there. Okay. Oh, and by the way, before I forget, that's not related to this problem, but I wanted to be on the record as well. I contacted JUMP yesterday about, you remember we had the exact Wilcoxon test. When we went for exact test, it was kind of crashing, right? The program was becoming unresponsive, right? So what I received as a reply was, I sent the same data set that was crashing my JUMP to Mia Stevens, who is the academic representative from JUMP. That crashed her computer as well. So she replied that, generally speaking, when you're performing, she read it somewhere in the scientific publications, when you're performing Wilcoxon test, it will run fairly quickly if your sample size is fairly small, so 20 or about 20, then you'll have it done fairly quickly. As the sample size is getting higher and higher and higher, it takes a long time apparently for the program to compute the p-value. The reason for that is the sampling distribution for the Kruskal for the Wilcoxon test is very weird. You have to pretty much like, let's say for example I have a sample of 3 and another sample of 3, so 6 numbers altogether, right? So what's the sampling distribution? Well, I'm going to have to perform all kinds of permutations, okay? So number 1 is in sample 1 or in sample 2. Same about number 2, number 3, etc. Okay, and therefore it will give me all kinds of sum of ranks in my possible samples, right? So therefore, if I have 6 observations, right, every one of them can be either in sample 1 or in sample 2. So it's close to, I guess, 2 to the power of 6. All right. If you're getting 10 observations, it's 2 to the power of 10. If you're getting 30 observations, it's 2 to the power of 30. So in other words, the computation of the sampling distribution, the exact sampling distribution, is becoming more and more and more computational intense. So much so that if you have samples of size, it crashed on us when I believe our samples were like 40 and 40. So it takes just too long to compute. That's why, remember when we did the Wilcoxon test, first thing it says, let's do the approximate test, right? It uses normal approximation and chi-square approximation. Why use approximation? For exactly that reason, right? Because it takes too frigging long time to compute the exact p-value, because computation of the sampling distribution is very computationally intensive. So therefore they're saying, let's not do that. Let's look at the approximation, like this is a normal curve. That's going to take us much, much quicker. Right? So the answers that you're getting are not exact science, obviously, but they're close enough. And you're saving yourself time computing. Because at the end of the day, what matters is p-value greater than alpha or less than alpha. That's all, right? So what if your actual p-value is 0.4, but approximated value is 0.37? It's going to be the same answer, right? So therefore, for the majority of cases, you'll get the same answer, reject null or keep the null, even if you're using approximation, okay? In some cases, yeah, you're going to miss. The p-value is 0.6, but your approximation is 0.441, 0.05 or 0.06, right? And 0.041. So therefore, with the actual test, you would have kept the null. With an approximated, you will reject the null. So there are things like that happen occasionally, right? But in most cases, that would make a difference. Okay, hold on, let me log back in.
So with a sample size of 40,
yeah, it's gonna
2 to the raised to the 40 is 1,100,000,000,000,000 permutations.
Yeah. Well, it's not the exact number because
And I rounded.
yeah, it's very computationally intensive. So that's why the program becomes irresponsive, right? Non-responsive, because it's just computing all the exact, all possible combinations, and therefore the shape of your of your sampling distribution. So it's not a pretty thing. So therefore, exact test for the not Kruskal-Wallis, Wilcoxon. It can be done only for small sizes, reasonably small sizes. Okay, and then it just hangs up the computer. All right. So there is nothing wrong with the program. I mean, there is something wrong with the program, right? I mean, we have to probably opt out for approximation instead of the exact test, right? In the majority of cases. Okay, well, let's go back to our exercise, right? People going to gym and getting addicted to exercise or not. Well, obviously, from my sample, from my data set that I'm analyzing two samples, right? Before, I told them to stay away from exercise, and after 3 days of physical inactivity, right? So I'm going to say that I am using, let's see, comparing two populations right here. Data type is ordinal, correct? Because the answers are 1 through 5, and that would be evaluate how I feel. And if the data are ordinal, I have two possibilities. If they're matched pairs, then sign test. If they're independent samples, then I have Wilcoxon rank sum test, okay, or simple Wilcoxon test. That's how JUMP calls it, right? All right. So what do you think? Based on what's written in my problem, it says we took a group of people and asked them how they feel, and then we told them to stay away from exercise and ask them again. That makes these observations what? Matched pairs, because that is how person number one was feeling before, right? They stopped the exercising, and that is how the same exact person was feeling after, right? 3 days of inactivity. Matched pairs, same person, right? On a specific person who was avid, exerciser, what kind of effect do we have? Okay, so therefore we have matched pairs, and therefore I have to use sign test. Now let's formulate the, so that answers questions A and B, right? What data type, ordinal, design, matched pairs, and what the test for the data, sign test. So now let's formulate the test. So what are we trying to see? We're trying to see if you can get addicted to exercise, right? So much so that you stop exercising, you feel worse, right? That's basically what addiction means. So therefore, essentially, here's my alternative. Let me start a new one. My alternative basically is going to say that the location of population after 3 days of inactivity is where? People start feeling worse, right? That's my assumption. To the left, okay? Is to the left. from location of population before they stay away from exercise, right? Make sense? And of course, null is that the locations are the same, right? The locations of before and after are the same. Before and after 3 days. After 3 days are the same. That's what I'm testing. Okay. All right. Now let's go to jump and let's test it. So over here, where did I go? Into the analyze, right? And then specialized modeling, right? That's where my matched pairs are located. And then I pick matched pairs. And I'm going to say, remember how it's done? I pick whatever I pick first goes actually second, right? So I'm trying to see if my before is to the right from after, or other way around. After 3 days is to the left from, it doesn't matter, right, how I pick them. So let's go ahead and pick after 3 days and before, so that way it's going to be before minus after 3 days, right? So I click OK. And here is my, well, it doesn't mean much actually, right? Yeah, so now I have to go ahead and look at that. It does the test on before minus after. Before, people are supposed to feel happier, right? Better. So in general, I'll have more 3s and 4s, right? And 5s. And after probably 3 days of physical inactivity, I'll have more 1s and 2s. So before must be to the right or greater than after, right? So therefore, that difference must be greater than 0, right? So I'm testing right tail. If this is what I'm testing, before minus after, before must be higher, so therefore I'm testing the right tail. So I go to the red triangle and pick a sign test, and the sign test gives me 3 possibilities, right? Less than m, that's left tail, greater than m is the right tail, and greater than absolute value, it's right and left tail. So I'm testing the right tail right there, okay? And the p-value is very small, so therefore, between my null and alternative, I reject the null in favor of alternative. And what do I have? Is that true that you become addicted to exercise? Statistically, it looks that way, right? Because if you stay out of exercise, your ratings are going to be smaller than before, or which is the same. Before ratings are higher than after 3 days ratings, okay? And there is a physiological reason for that, okay? When you exercise, your body starts pumping up endorphins, right? Feel good. Well, it's not hormone, it's more like a neurotransmitter, okay? So it's rebalancing brain chemistry, really, and getting more serotonin, getting more dopamine, the reward neurotransmitter. And after that, you feel more energized, you feel, that you can do everything and anything. So that's how exercise basically works. Okay? Make sense? Any questions? Fairly straightforward, right? Okay, good. So that was problem number 1. Okay? Did you get it right when you did the exercise yesterday with this practice? Christian?
Yeah, I did, for the, more or less, I got the additional, I said, I didn't like specifically say the location of before and after 3 days of the same. It says the change. So I said that evidence suggests, or for the alternative, I said there seems to be a correlation between exercise and
Okay.
Can I do that?
No. Correlation basically, what kind of test is correlation?
DFT?
No, we learned it yesterday. When you're correlating things, you're talking about Spearman rank correlation test, right? So essentially when you're saying, if, this goes up, that goes down, there is a relationship, then you're talking about relating variables x and y. So it's not comparing populations, it's whether or not they're linked together, the variables, right? So it's a little bit different animal. So in other words, what you did is, in this flow chart, instead of comparing two populations, right, you went over here and you said, analyze the relationship between two variables, right? And that will lead you to Spearman-Rank correlation test, right? So we're not trying to see if before depends on after or other way around. We're trying to see how they compare. Essentially, it's like same thing, but we're hoping that we're hoping to see that if you stay away, then you shift the distribution, right, to the left to the smaller numbers, and that would be just comparing two populations. Okay. All right. So let's take a look at question number 2. Tom Frederick is the computer support manager for a large company whose employees have been complaining about spam, which is known as, well, you've seen spam, right? By, timeshare at the resort and whatever, right? So some stuff falls down. And most, like if you're using Gmail, most of the spam is being filtered, right? There is a spam folder. You probably very rarely, if ever, look in the spam folder, but if you look there, you will see a bunch of crap inside, right? And most of that is sales offers, things like that, right? By the way, most of the spam on the internet is not, there is nobody who sends this email. It's being sent by robots, right, essentially, by the software that automatically generates that stuff, right? Okay, so spam is plugging the organization. Tom asked a sample of 40 people to keep track of number of spam messages they received during a week. Then he installed, and all this information obviously is recorded, right? So let's take a look at that. Spam right there. So let's open it up, and what do we see? 40 people, right? Person number 1 said he received 28 junk emails during the week, and then 27, 24. So these are the numbers, okay? And then he installs the spam filter software into the email system, so that every time when the email comes through, they classify it as a legitimate or a spam, and if it looks like spam, they're going to filter it out, right? But that should decrease the number of spam messages, right? And then, if filtering software is effective, the number of spam messages should go down. During the week following the installation, he asked same employees, same is the keyword here, agree? Same employees, to keep track of number of spam messages they received, and the results are recorded in the file. So therefore, in my file, after filter is installed, this second column, essentially same people report during a week how many spam messages do they receive, right? Well, same series of questions we go through, right? What's the data type, how data are collected, and based on that, what do we use? Okay, so let's start with our flow chart, beautiful flow chart. Is it obvious that we're comparing two populations? Again, fairly obvious, right? Before and after, what's going on? We should see the reduction. Okay, data type interval, that's also obvious, right? Counts of spam messages, right? Like we discussed, variability is no concern for us, right, in this class, so we're looking at central location. What do you think about experimental design? Matched pairs, right? Because of this keyword, same, right? It's the same person, okay? Because what can happen if I use independent samples, 40 people and 40 other people. Some people may browse internet more, right? And basically, the more you browse, the more sites you visit, right? The more of them think that you're interested, and probably you will receive more spam messages, right? That could be the logic behind that. But we're looking at the same person, right? So now we're comparing, not just without any mixture of other factors, such as different browsing habits, right? Same person, before the filter was installed and after, how does that compare? Okay? So therefore, I'm having matched pairs. And the next question is how the differences are distributed, right? So now I have to compute the differences and see if they're normal or not. If they're normal, and it's a t-test. If they're not, well, Coxon signed rank sum test. Well, let's do that. So over here, I'm going to create a new column. Let me call it column of differences. Differences. All right, differences with two F's, right? Okay, and I'm going to type the formula, edit the formula, and that would be, doesn't matter, right, how I subtract first minus the second or other way around. Either way, it's going to be normal or not. So I'm going to say before filter minus after filter. And then I click OK. Okay, here are the numbers. And let's look at the distribution. All right, so distribution, and I pick differences, bring them over here, click OK. And there is my distribution. By the looks of it, what do you think? Am I going to have a normal distribution or not? Doesn't look that way, right? Now let's check out the normal quantile plot. And it's weird, right? It's all wiggly waggly. Now let's be formal. Let's run the Wilcoxon Shapiro-Wilk test, right? So I'm going to go continuous fit, normal curve, and you can see that normal curve doesn't fit well. So therefore my Shapiro-Wilk probably will show that. Okay, so goodness of fit, and indeed Shapiro-Wilk p-value, very little, right? So therefore I reject the null, that the data are normal, and conclude that differences are not normally distributed, unfortunately. So therefore, coming back to my flow chart, meshed pairs, right? We decide these are meshed pairs. Differences are non-normally distributed, so I have to use a non-parametric test. Agree? Wilcoxon signed rank sum test. Okay, so now let's formulate what exactly am I testing. Okay? So I'm trying to see if the software spam filter, right, helps to eliminate spam. So average number of spam messages should decrease, right? So before I install the spam filter, it should be higher, right? So therefore my null or alternative, I start with alternative, right, is that the location of population before filter is where? To the right or to the left? Before the filter was installed. Before. To the right. It was supposed to be high, right? Supposed to be more. Is to the right from after filter. That means that filter removes away some, at least, of the spam messages, and therefore, overall, I see smaller numbers, right? And therefore, my null hypothesis, well, null is always the same, right? The locations are the same. The locations of before filter and after filter. And after filter are the same. That's what I'm testing. Null and alternative. Okay? So now I'm going to go back to jump and do the test. Now this time around, I'm going to use actually the same exact thing, right? Because in the first problem, I had meshed pairs, same person. And here, I have meshed pairs, same person, really, that's the matching criterion, right? So analysis is basically the same. It follows the same steps anyway. So I go to Analyze, Specialized Modeling, Meshed Pairs, and I want the before to be number 1, so I pick it second, right? So I pick after first, and before second, because jump reverses that, right? And then I click OK, and indeed it says we're testing difference before minus after. Before is supposed to be higher, right? So the difference is supposed to be positive. So I'm testing the right tail, okay? But I need to call up. Right now it shows me the t-test, assuming that I'm dealing with normally distributed differences, which is not the case. And I'm going to go to the right triangle menu and ask. In the previous problem I asked for sign test. Now I'm going to ask for Wilcoxon signed rank test, right? Kaboom, and there it is. So I'm looking in the right tail, and once again my p-value in the right tail is very small, less than 1%. So therefore I reject the null, right, in favor of alternative. And my alternative says what? Is spam software effective in reducing the spam? Yes, it is. Statistically, I have less spam with the spam filtering software. You know how spam filtering software works? It's actually artificial intelligence kind of algorithm, also called neural network. So essentially, it's a self-learning algorithm. Let's say I received an email, okay, and it wasn't filtered out for some reason, okay, because software didn't know how to classify it. I filter it out, and after that, the algorithm looks at the content, looks at the words inside the message, things like that, and then it creates a rule, basically. So it adjusts itself that, hey, if things like that come up or similar, then I have to filter it. So essentially what happens is every time when it receives an email, it reads the content of the email, and based on the algorithm, it calculates the probability that this is a spam. If the probability is very high, less than or greater than 50%, then it's getting filtered out. If the probability is small, less than 50%, it goes to the inbox. That's how filtering software works. So artificial intelligence, really. Okay. All right. So that was our problem number 2. Make sense? Any questions? Should be fairly straightforward, right? Okay, I'm going to close that out. Let's look at the problem number 3. Problem number 3 is also fairly cool. Environmental Protection Agency is monitoring how nicely the industrial liquid waste is purified before it's discharged into the water. So essentially what we're saying is there is a plant sitting on the river, right? For their process, whatever they do, they take the river from the water, they use it in their production cycle, and then after that they say, oh, okay, so it's dirty now, let's filter that, let's put it through the ultraviolet radiation thing to kill the bacteria, right? And then if it's pure enough, let's dump it to the water. So the local plant manager claims that the plant purifies the waste to such extent that it does not pollute the local river where the water is being dumped. The EPA inspector would like to check this claim. He collects a number of water specimens in the river upstream from the plant, where the water is supposedly pure, right? And then in every sample they count the bacteria. So they put it under the microscope and count how many bacteria they see in the sample, right? Then he does the same thing in the river or in the liquid purified discharge of the plant. So the water that is ready to be dumped back into the river, right? He goes to this tank and picks up number of samples and does the same thing, count the bacteria, right? So for the plant to be compliant with EPA regulations, the average bacteria count in the purified waste must be no more than the than in the pure river water. Okay, so if it's over that, then we're violating the regulations, right? But if it's no more than that, then we're not violating the regulations. Okay, cool. Same set of questions. What type of data are being studied? What design and what kind of analysis do we perform, right? Based on the normality properties. So let's take a look at the data. Where is that? Liquid waste, right there. So I'm going to open it up. And there it is. So samples in the waste, in the purified waste, the counts were 52, 34, 49, different counts obviously, right? And in the pure water, that's it. Okay? All right. So let's take a look at my chart. So once again, where do I start? comparing two populations, right? Data type, interval, agree? Numbers count. So I'm looking at the central locations. Independent sample or matched pairs? Independent, right? There is nothing that links sample 1 and sample 2 on the same line, right? It's just I go to the river and make 40 random samples, right? 40 vials of water, and then I go to the tank that contains the purified waste, and I get the 40 samples, right? 40 specimens. So therefore, samples are really independently collected. There is nothing that links one sample to another sample, right? So independent samples, and therefore now I have to look at distribution of every single one of them and see if they're normal or not. Well, let's do that. I go back to the file, right, and look at the distribution of both waste and the pure water, and then click OK, and there it is. It's hard to tell, right? By looking visually, that maybe looks normal. That I don't know, to be honest. So let's not take a chance, and let's look at the normal quantile plot. That's actually very decent, right? Very nicely aligned. So therefore, I think this is normal. How about the pure water? Pure water was looking a little bit more non-normal, right? But it's actually fairly decent. So do you want to go and do the Shapiro-Wilk test, or are we going to say, no, they look good enough? Probably normal, right? Probably normal. So I'm going to say that normal and normal, so I'm good to go. Therefore, it's my good old buddy t-test, right? All right. So let's write down the hypothesis. So what am I testing? Being an inspector is always looking for things, for violations, right? If they report that everything is okay, that probably it's like same mindset as auditors, right? Auditors are looking for violations, really, right? They're checking everything to find, did you record this transaction correctly or not? Did you record that transaction correctly or not? The same thing here. So my alternative hypothesis would be what? That the plant is violating the regulations, right? And violation means what? Average count of bacteria in the waste is higher than the average count of bacteria in the pure river water, right? So my alternative becomes that the plant is in violation, okay? So average count in the purified waste is higher than the average count in the pure water. In this case, I'm going to write them the fine and make sure that they don't do it again, right? So they are violating the regulations. Or alternatively, it translates into the following form: mu waste minus the mu for the pure water is greater than 0, right? That would indicate the violation of regulation. Okay, so therefore my null becomes that they're compliant. Okay, no more than in the pure water, which means greater than or less than or equal to, right? So null is going to be that the count of bacteria in the purified waste minus the count in the pure water is less than or equal to 0. In this case, they're compliant, right? Null means compliance, alternative means violation. Okay? That's what I'm testing. All right, let's go back to JUMP and do the test. So samples are independent, which means I need to do what? Stack them, right? Every time when you're dealing with independent samples, JUMP requires stacking. So stack. I'm going to do waste and pure. So data I'm going to call bacteria count. And the label I'm going to call, oh God, how do I call purified waste and the pure river water quality. Yeah, it's more about where do you test it, right? Do you test it upstream or the location? Yeah, location where you pick a sample, right? In the river or in the waste tank. Okay. So this is it, and after that I have to do fit y by x, right? So I'm studying really the effect is the location, which is a factor of study here, right? Does the location where I pick the sample have any effect on the bacteria count, right? So my response is bacteria count. My location where I pick samples is the factor of study. And when I click OK, there it is. Even visually, it looks like bacteria count actually is higher in the waste, agree? Because the samples are so far away. All right, let's take a look at the summaries, mean and standard deviation. So what do we see? In the pure water, 39 samples. In the pure water, the mean was 30.8. In the waste, the mean was 42, right? And the standard deviations are 6.6 and 5.4. Are standard deviations fairly similar, or are they horrifyingly different? Fairly similar. So I'm going to use the assumption that the variances of the samples are the same, right? So I'm going to go to the menu and say pooled t-test, assuming equal variances. That's what the test is going to tell me, right? Assuming equal variances. So I am looking at waste minus pure, right? That's what it's testing. So according to my alternative hypothesis, right, waste minus pure must be greater than 0. That's the alternative, right? So I'm testing, again, the right tail of the distribution, right? So waste minus pure, right tail of the distribution is where? Right here, okay? So very small p-value. All right, so I'm an inspector. What do? Small p-value, reject the null in favor of alternative, right? And my alternative says that statistically, you guys, you're looking at a much higher count of bacteria in the waste as compared to the pure water. So it looks like statistically you're actually violating the regulation. So here's the fine for you. Right? Make sense? Any questions?
That was just a regular t-test.
Yeah, it was just a regular t-test because samples are normal. Patrick?
Why did we do means and ANOVA dual T rather than just...
Yeah, let's do that. So right now, you see that we picked the test, this option, pool T. Pool T, basically you do the pool T when your standard deviations are very close. And that's why we are looking pretty much at the standard deviations first, just to judge them. Where did we look at them? Right? Yeah, here, standard deviations. Just to judge how close they are. If one of them would be 5 and another would be 3, we're going to say, wow, standard deviations is half of the size of the previous one, right? So they are unequal. In this case, we would go ahead and do the other test. It's this t-test, okay?
So if there was a big difference between them, we do that.
And let's run it. So if we run this t-test, and I'm assuming it's going to get at the end. Yeah, you see that? It's testing same thing for me. Waste minus pure, but there is a sentence here that says assuming unequal variances. And let's see if unequal variances give us the same result or different result. I'm testing same hypothesis, right? So I'm still looking in the right tail. And look at that, p-value is still very small, right? So in this case, it doesn't matter which test I would use, equal or unequal, it will result in the same answer, okay? All right, so now let's go to problem number 4. Problem number 4. That's a cool one. Can gasoline mileage, performance of the car, MPG, miles per gallon, be predicted using car's physical parameters? So the file MPG contains data on sample of cars from 2002. For every car we have MPG, horsepower, width of the car, and weight of the car in pounds. Okay. Now, you know that how much, what kind of effect horsepower has on the MPG? You know?
Yeah. Greater horsepower,
The less miles per gallon, right? Because horsepower translates into number of cylinders in your engine, right? And cubic centimeters, like volume of your engine, right? and therefore the consumption of fuel is higher. Muscle cars, basically that's the principle, right? They have more cylinders, they consume more fuel, so therefore their fuel economy is actually pretty bad. Okay, so that's what we expect to see. Now let me go ahead and close all these things. Okay, so that I don't deal with many windows. Alright, MPG. Here's the file. And I'm going to open it up. And there it is. So, first question asks me to go ahead and develop a model to predict the average fuel economy based on the car parameters. So, therefore, what technique should I use? Let's see. Here I'm talking about analyzing one population, or comparing two populations, or comparing three or more populations, or analyzing relationships between three or more variables. What do you think? Where do I start? Relationship, right? I'm trying to see if car performance in terms of MPG is related to the horsepower and all these things, right? So analyze relationships. Data type, obviously, they're all interval, right? They're all numbers. So therefore, I'm talking about multiple regressions here, right? And I wouldn't be able to even compare them because quite literally it's apples and oranges, right? MPG versus horsepower, completely different things. Units are different, right? So I wouldn't even dream to compare them. It's not ANOVA, okay? That would be wrong. All right, so how do I develop my regression? Fit the model, right? Okay, so what's my target in this case? Or dependent variable? What am I trying to predict? Miles per gallon, right? Trying to predict the performance right there, miles per gallon, based on horsepower, width, and weight. So these are going to be my effects. Okay? And when I run the model, there it is. Okay, so let's see what the equation is. Equation is 33.11 plus very small number times the horsepower. So MPG, to predict MPG, I have to take 33.11 plus very small number 0.301684 0.301684 times horsepower. Okay. Then plus 0.0839 times the width and minus, if I remember correctly, 0.0052 times the weight. That's my regression equation, ladies and gentlemen. Okay? Alright, so let's take a look at next question. Assuming that all required conditions are satisfied, is this a valid model? To receive full credit, clearly state hypothesis, p-value, and your conclusion. So how do I test model validity overall? Here is the test that I'm performing. My null is going to be that the slope for the horsepower, I'm going to call it HP, is equal to the slope for the width of the car, is equal to the slope for the weight of the car, is equal to 0, right? So in other words, I can eliminate all variables from my equation, and the equation and my regression will not suffer tremendously, right? So therefore that makes the model invalid. And the alternative is going to be that at least one, now let me write it out, at least one slope cannot be set to 0. So at least one of the variables is actually linked with MPG. Okay? That's what I'm testing for the model significance. And after that, let me go back to jump and find the p-value. The p-value is right here. Analysis of variances, right? Standalone p-value. And I see that it's very small, right? So therefore, I reject the null in favor of alternative. And therefore, I'm going to say that the model is significant, right? This is a statistically significant model. It's a valid relationship, right? Okay, the next question. If the car manufacturer redesigns the car, this one is twisted a little bit. If the car manufacturer redesigns the car so that engine horsepower stays the same and the width is the same, but they're using lighter materials for the parts, okay? And the car gets lighter by 400 pounds due to the use of lighter materials. What effect will it have on the car's average fuel economy? Well, what do you expect? If the car is getting lighter, will MPG go up or go down? It will go up, right? Okay. So let's take a look. All right. The weight of the car actually has a negative sign, right? Which is a good thing because it says if weight goes up, MPG goes down, and other way around, right? So how do I interpret that number, the slope? Very easy, right? If the weight goes up by 1 unit, so weight plus 1 pound, okay, then the MPG of the car will go down by what? Minus 0.0052 miles per gallon, right? So every pound increase of the weight results in the reduction of the MPG, okay? So that's per pound, okay? What happens if I reduce the weight by 400 pounds? Essentially, I'm subtracting 400, right, from my weight. So therefore, I have to multiply my minus 0.0052 by minus 400, agree? That's my change of weight, okay, in the car. And whatever that turns out to be, that's my impact. So it looks like it's going to be 2.08, right? Oh, because it's 4 times 100, so you eliminate 2 zeros from here, and you move your decimal point over here, and then multiplied by 4, and you get 2.08. So you reduce the weight of the car by 400 pounds, your MPG goes up by 2.08 miles per gallon on average. Make sense? That would be the effect. Okay? All right, let's keep going. Assess the model accuracy, how well the model fits your data. All right, let's do that. And here in this part, we're talking primarily about the R squared, agree? Okay, let's go to R squared, summary of fit. My R squared is 0.7482, almost 75%. So my interpretation of this is these 3 variables, variability between these 3 variables, weight of the car, the horsepower, and the width of the car, their variability explains about 75% of what's going on with MPG from car to car, right? So this is a fairly decent model, right? I have only 25% of the variability of different MPGs unexplained. So some other things contribute, right? Such as, I don't know, aerodynamics of the car. Okay, how high is the air resistance? Okay. Oh God, I don't even know what else can. I'm not a car expert. So some other things contribute to the rest. Okay, maybe the engine design. I mean, horsepower is great, but how it transforms the torque into the rotation of the wheels, something. Okay, some other mechanical part. But these 3 variables by themselves explain 75% of what's going on. So this is a fairly decent, very very decent model actually, pretty accurate. Okay. All right. For every independent variable, comment if the variable is making significant contribution into the model. It will use 5% significance level, and provide what hypothesis you're testing, etc., etc. So here, I'm going to test every individual variable, right? So for the horsepower, I'm going to say horsepower is not a significant variable, that's my null. And the alternative is going to be that no, horsepower you have to keep as is, cannot be set to 0, right? And I'm going to do the same for the width. Null is going to be that the slope for the width can be set to 0. And the alternative is going to be that the slope for the width has to remain as is, non-zero, and that's a significant variable. And my null for the weight, slope for the weight is equal to 0, and the alternative is going to be that no, slope for the weight has to stay non-zero. 3 different p-values, 3 different conclusions, right? So let's go back to the jump output. Okay, there it is. Let's see, horsepower, 0.9746. Oh gee, that means that horsepower is not really a significant variable, right? 0.97 and 0.34 the width. So 0.97 greater than 5%. So I keep the null, and therefore horsepower, amazingly enough, is not a significant variable. This one is what was that, 34? Can't remember, 0.34, right? Same thing, right? Greater than 5%, keep the null, not a significant variable. And the weight of the car is very small, okay? So it's less than 0.0001 p-value. So therefore I reject the null in favor of alternative, and it turns out that between my 3 independent variables, looks like weight is the only one that's important. The heavier the car, the less the MPG. Which is a little surprising because you would think horsepower will play a role, right? Maybe not the width of the car, but the horsepower definitely should play a role in the MPG. Okay, but according to our model, it doesn't. Okay. Oh, it's because this is a made-up data set, obviously, right? Okay, the last couple of questions. For a car that has a horsepower of 150, the width of 70 inches and weighs 300 pounds, what's the expected MPG? Well, I can actually plug in the values into the equation, or in JUMP I can use the profiler, right? So I just call up the profiler right here, and I say weights, the car weighs 3,000, 150 horsepower and 70 inches. So horsepower is 150. Okay, the width is 70 inches, and the weight is, what is 3,000? Yeah, 3,000. Okay, so there it is. This car will run at 23.3 miles per gallon on average. That's my point estimate of this fuel economy. Make sense? Okay, very good. Finally, check all the required conditions to see if this is a useful and usable model. What are the required conditions? Number 1, residuals must be normally distributed, right? And then residuals must have a nice plot, and then there is multi-collinearity. So let's start with normality of residuals. So I go back to my output, and I say, well, let's save residuals in the file. So I go to the red triangle, say save columns, and save residuals. And now I go back to my data set, and here is the residual column for me. So I'm going to look at the distribution, right, of residuals for MPG. Click OK. What do you think? Is it a good looking plot? Yeah, it is. In fact, let's run the quartile, normal quantile. So only a few points on the high end, and maybe these couple of points which are outliers, right? According to my, here is my box and whisker plot, right? Right at the bottom. These are outliers, cars with unusually, I guess, low MPG and unusually high MPG, right? But I got to tell you that if you have 120 points and you have only 4 outliers, that will not make a big splash, right? So we can run the rigorous test, and it will show probably that things are normally distributed. So I'm good on this side. Okay. Let's go back to the output. So here is my residual plot, right? Okay, trying to remember what I'm trying to say. Residual plot, okay? Do you see any patterns, lines, heteroscedasticity? Looks like a random plot, right? I don't know if I can see any kind of nonlinearity or trend or line or curve. Residuals also remain about the same thickness, right? Here and here. They're not uniformly distributed. Yeah. So these 2 points, it looks like they're screwing up the picture, right? But I'm willing to bet you that, remember, we had 2 outliers, on the high side and on the low side. So I'm willing to bet that these are 2 of your outliers, and these 2 points probably 2 other outliers right there. Okay? So therefore, I'm not too concerned about the shape. Okay, so it looks fine. Now, the last thing is your independent variables should be truly independent, right? Okay, so let's go back to the original file. And how do I evaluate that? I have to call up correlation matrix, right? So I go to Analyze, Multivariate Methods, and pick an option Multivariate. And here I have to correlate only independent variables, right? I want to see if they're truly independent from each other. So I'm going to pick only horsepower, width, and weight. Click OK, and here is my plot. What do I see? Unfortunately, I see a lot of correlation, looks like, right? Because all of my ellipses, correlation ellipses, look fairly focused, right? Fairly narrow. So width and weight is probably the worst, right? Because it has the highest correlation, looks like. They're all fairly high. Well, now let's evaluate them. Horsepower and the width, 0.64. Remember when we declare the problem? 0.7, right? Or minus 0.7. That's where it starts. So we're kind of on the brink of the high correlation here, right? Not quite, but it's pretty strong, right? So we're going to say that's not a problem yet. Even worse is horsepower with the weight, right? 0.689, basically 0.69. That actually is a red flag right there, right? And clearly there is a red flag between the width and the weight. And that makes sense, right? Because your car gets wider, it becomes heavier. That's pretty straightforward, right? Now, it's not so clear what's the relationship between the horsepower and the width, why they're highly correlated with each other. Right? Because the horsepower has to do with the engine, right? How is that related to the width? I don't know, quite don't know. Well, maybe you're getting a bigger engine, additional, 2 cylinders, the engine becomes wider, the car becomes wider, maybe something like that. But the correlation isn't strong over here. Okay, so the only problem, obvious glaring problem, is this one, right? Width and the weight. But we found that width is not an important variable, right? And the horsepower is not an important variable. So if we eliminate them, by the way, let's do it. Okay, so the result of this analysis is that I do have a problem, right? I do have multicollinearity. There are 2 variables that are highly correlated. Shan?
I'd like to confirm. So we're looking at a coefficient of correlation closer to 1,
Or minus 1.
absolute value of 1. The closer the coefficients are multi-correlated, which is the bad thing.
Well,
The closer that they are correlated to one another
yeah,
is saying that they are collinear,
collinear.
which is our problem.
Yeah, which is our problem. That's right. Yeah, so high correlation coefficient is a problem, right? So let's go back to the analysis. Oh, I closed it, right? Now it's actually very easy to reproduce. If I go fit model and just say recall, it gives me the same settings. Now I run them. Okay, so 2 things that I can eliminate apparently are what? Width and the horsepower. So let me take horsepower and remove it. And let's remember that R squared is 0.75, right? If I remove the horsepower, what happens to R squared? Practically nothing, right? 0.748. Didn't make a splash. Now I take the width and eliminate that. still 0.746, right? So that's another confirmation that these variables are not contributing. If I remove them, goodness of fit is not being affected practically in any significant way, okay? Make sense? All right, good. Christian?
So when we just write, check the, so we check for the multivariable method
Uh-huh.
for the multivariables and see what relates to what. So with, have a high correlation, meaning that they're both not significant, and we just deleted those.
No, they're not significant. That means that they're telling you the same story
Yeah,
pretty much.
yeah, that's what
Yeah.
it is.
One of them is actually non-significant, which is the width. Another is significant, which is weight.
Yeah.
So therefore, when you decide, like the fact that they're highly correlated essentially tells you that both of them should not be present in the model, right? Because you know one, you pretty much know the other. Which one do you eliminate? The one with a high p-value, right? So,
So we basically just write that out.
mm-hmm. Yeah.
So it's actually giving you the best fit model in the exact summary,
Mm-hmm. Yeah.
because it's giving you the weight followed by the width by the source
Yep. It ranks them in the order of reducing importance, so to speak, right? So if you go to the analysis, let me do it again, right? No. Oh, I closed it. Okay, so right here, when you do the analysis, let's see if it remembers. Yeah, it does. Okay, the effect summary, this part, pretty much it tells you what to do, right? It says that the highest order of importance is the weight. It has low p-value, so it has to stay. And then after that, you can use your judgment. So this is high p-value. I eliminate it first. And it recomputes, obviously, the p-value. And the equation is different now. So next one, width is still not important. I eliminate that. And the remaining variable, effect summary. Remaining variable is still important, the weight. Okay?
The log work has gone up. What is the log?
Log worth is just some measure that they calculate. I don't quite remember what it means, quite honestly. Yeah. So it's not part of what we're looking for in statistics, with this part of statistics, right? Standard statistical course. So, all right. Let's do the next problem. USA Today explored what male workers say is a most important aspect of the job. The survey conducted reveals that 36% of people say good relationships with the boss. 21% report resources to do the job. 19% people report that easy way to get to work is important. 15% flexible hours, ability to come in late and leave late. Right? And 9% said they like to work from home. Telecommuting, that's what it's called, right? So they want to see if the same percentages are also valid for women. So we take these as a basis, right? And then we say, well, let's take a look at 500 women and see if these things are important for them as well, okay? So let's formulate our null and alternative. Well, first of all, let's open up the file, okay? Where is that? That's job, right? File with jobs. Just like that. Okay, so here is my data. So these are the results of the survey among women, right? Okay, good. Let's take a look at how these things are distributed. So I call up the distribution and click OK. All right, and there it is. Let me go ahead and stack that. Cool. All right, so it looks like that among women, 38% say good relationship with the boss, when for the guys it was 6%. So there is a slight difference there. 22.8% resources to do the job versus 21. Then we have 16% said easy commute. Among the guys it was 19%. 15% of guys said flexible hours at work. Among women it was not 15 but 17. And lastly, ability to go to work, to do work from home. 6% of women like that, and 9% of men. So they're fairly close, right? But we don't know if they're quite the same or not, statistically, right? So therefore, first question is formulate your null and alternative to see if men and women are different in how they perceive what's the most important thing for the job. Now let's be formal about that again. What are we doing? Am I analyzing one population or comparing two populations or three or more, or is it a relationship? What do you think? Well, two populations, I should have two samples, right? I have only one sample. So really, I'm looking at one sample and comparing the breakdown of percentages against certain percentages that I view as a standard thing, right? So therefore, really, I'm analyzing only one population here, okay? Describe a population. I start here. Women, right? How they respond to this survey. Data type, interval, ordinal, nominal. What do you think? Nominal, right? Responses, 1, 2, 3, 4, 5. You shuffle them in any way, it's the same thing, really. Nominal. Number of categories, do I have 2 or 3 or more? 3 or more, 5 specifically, right? So therefore, I have to use chi-square goodness of fit. Okay, so here is my null and alternative. Remember we did that some time ago, right? In my null, I'm going to say that women look at the job in the same way as men. In other words, the proportion of people who said 1, that was good relationship with the boss, right? Men, it was 36%, right? Response 1, 36%, right? And women, I'm going to say, are the same. So they are 0.36 for the good relationship with the boss. Second proportion, number 2, was it 21%? That was 20. No. That's for women, right? But we're saying that proportions for women are the same as for men. 21, right? And what was the second response? I forgot. 21% said resources to do the work, right? 19 easy commute, and we're assuming that women are the same, right? So proportion number 3, P3, easy commute, 19% of women like that. And then the next one is number 4, flexible hours, 15% and 9% ability to work from home, right? So flexible hours, P4, 15%, and ability to work from home, P5, 9%. So we're saying that these are proportions for women, same as for men, which means that men and women view the most important aspect of the job similarly, right? Christian?
The results for women actually expected values for men. As opposed to just females.
Yeah. Yeah. But if you write it out, then yeah, it's the same thing exactly. Then this way I can see that you understand exactly what's going on, right? So, and alternative would be no, they don't match, and maybe not all of them, right? So therefore, I'm going to say at least one of the proportions, Pi, for women differs, right? Differs from that for men. In other words, men and women, they do view things differently. Maybe one of the aspects, maybe two of them, right? Like we discussed, it's a zero-sum game, right? If one of them gets higher, another gets lower, right? Because they should adapt to 100%. But at least one is different, okay? So there are two ways how to do this problem, a quick way and a short way. Which one do you prefer? I'm sorry, yeah, I said the same thing, right? Quick and long, right? Quick way and long way. Which one do you prefer? Quick? Okay. So quickly, here's the quick test. Okay? If we want just the software to do the, mechanical piece for us, right? Oh, crap. Okay. Let's go back to the software. Right there. Okay. So, very straightforward, right? I go here and I say, I want to test probabilities. Kaboom. All right? And my probabilities are hypothesized probabilities, right? So 0.36 for good relationships with the boss, 0.21 for resources to do the work, 0.19 for easy commute, 0.15 for flexible hours, and 0.09 for the ability to work from home. Okay? And when I click the Done button, it says Pearson, right? I'm looking for Pearson goodness of fit test. 0.038. That's it. Probability greater than chi-squared in the right tail of the chi-squared distribution. 0.038. So, what do I do with 0.038? 0.038 is less than my standard 5% significance. So therefore, I reject the null in favor of alternative. And what do I say? Are men and women the same when it comes to the job aspects? No, they're not. Right? So even though these differences in percentages that we saw in the file, right? Let's go back. They're fairly small, right? Here, you'd say only 2% difference. Not a big deal. Here, less than 2% difference, right? Here you have 3% difference. You wouldn't think that this is a great difference, right? But software says, well, statistically it is. Okay? Even though there are adjustments, small adjustments here and there, that actually indicates that there is a statistically significant shift in perception. Make sense? Okay, good. So that was problem number 5, right? Number 6. A construction material company that manufactures concrete wants to see if the properties of concrete change over time. It can happen, right? Over time it can become more sturdy or more brittle. Whatever happens, right? We can basically, we can build theories, right? But practice is the criterion of the truth, right? So one of the concrete properties is the ability to withstand compression. So the company, here's what the company does. They make 120 samples. And then samples solidify, and they take 40 of them 2 days after the samples were made, and apply pressure on them and crush them, right? And record how much compressive strength it takes to crush the sample. So 40 samples are destroyed, and they record what's their ability to withstand pressure. Then after that, they take other 40 samples. It should be a week, right? 7 days. Yes, 7 days after pouring the compressive strength for another 40 samples is measured. So they take 2 days, measure the 40 samples, and 7 days, measure another 40 samples, and then after that they take 28 days, 4 weeks, right? And destroy the last 40 samples. Is there a difference between compressive strength? In other words, what we're trying to say is, do the properties of concrete change over time? That's essentially what we're trying to investigate, right? Okay, so I'm going to close out all the stuff that I don't need, and let's go and take the concrete strength sample. Concrete strength. Right there. Okay, so let's be formal. Statistics is a tool set. Let's pick a tool. What do I do? Compare 2 populations, 3 or more, or is there a relationship problem? What do you think? Where do I start? Even by looking at my data, I have 3 columns, right? Which means I'm really comparing 3 populations to each other, right? So therefore, let's go back over here. Okay. Data type, interval obviously, right? Because these numbers represent measurements. Agree? How much strength it took to destroy a sample. So it's, I don't know what are the units. Okay? Alright. So interval, data, experimental design. I have independent samples or blocks with replicated measures. What do you think? That goes back how the data was collected, right? What did they do? They made 120 samples, then they took 40 of them, destroyed 2 days after, and took another 40, destroyed 7 days after, and they took the last 40 and destroyed 28 days after, right? What do you think? Is there anything that links observations on the first line, observations on the second line? In other words, do these things have something to do with each other? It looks like nothing really, right? They took 40 pieces of concrete and broke them. Then they took 40 other pieces of concrete and broke them, right? So there is nothing really that links these observations together. So I'm dealing with independently collected samples, right? Okay, so let's go back to the flow chart and independent samples. Now the question is, what do I have? Normally distributed samples or not normally? Because if they're normal, that's one-way ANOVA. If they're not normal, that's non-parametric analog. That would be Kruskal-Wallis test. Okay, so let's test normality. Go here and we say distribution of 2 days, 7 days, and 28 day samples. Alright, so here is my distributions. Yeah, I see some weird stuff, right? Especially sample number 1 doesn't look too promising, right? That may suck. Okay, so let's go ahead and investigate its normality. This part is okay, but here I have some weird pattern, right? So let's actually go for Wilcoxon test. We can kind of judge that visually, so let's go with the formal. Fit to normal distribution. Where is that? Right here, normal fit. And here I perform goodness of fit test. Thank God it passes the normality, right? So even though I see this spike, that's not enough to screw up my normality. Okay, good. Now these two samples probably are okay. Let's just verify. Quantile plot. Yep, looks pretty decent. So it has the same wiggly tail over here, right? But the majority of points they fit nicely, so it's probably normal. And my 28 days normal quantile plot, that should be the best. Not so much. It also has the tail. Now let's run the Shapiro-Wilk test on this one. Let's see. Normal fit, and from the normal fit, I pick goodness of fit. Look at that. You see that? Red flag. So that means that this sample actually is not normal, right? Kind of glad that it's not normal, because that's just basically to show you that two samples can be okay, but if one sample is not normal, then the whole idea is out of the window, right? So therefore, fortunately, I have to say that populations are not normal, so therefore I have to use Kruskal-Wallis test. Okay? So let's go ahead and do this. What do I test? My null hypothesis. My null hypothesis is that samples are the same in terms of their compressive strength, right? In other words, the locations of population, what do I call it? 2 days after pouring, right? And then 7 days, and then also 28 days are the same. Okay? So in other words, the compressive properties of the concrete do not change over time, right? That's what essentially it says. Time has no effect on what strength does it take to break them. Okay? And my alternative, of course, is that at least two populations are different, right? At least two populations differ in locations. Okay? That's what I'm testing for the Kruskal-Wallis non-parametric test. Okay, let's go back. Independent samples. What do I do with the data? I stack them. I have to stack the data. And let's do the stacking. Tables, stacking the data, all three of them. Say okay. So the data itself I'm going to call compressive strength, right? Compressive strength. And the label is going to be versus time, right? Time. 2 days, 7 days, 28 days. Okay? So I'm investigating if time has an effect on the compressive strength of the concrete. When I click OK, it shows up my sample rearranged steps. And now all I have to do is go to the fit y by x, right? And cause and effect testing, right? So my measurement or response is compressive strength. The factor that I'm using as the factor of study is time. Okay? And when I click OK, there is, well, judging by these things, what do you think? What will the test show? Same or different? Judging by this picture. Probably different, right? Looks like first strength goes up and then it drops, right? Okay, so let's go ahead and do the summaries. Not that they're useful, because we said that one of the samples is not normal, right? So therefore, these things are not going to be useful for us, probably. So let's go ahead and go with non-parametric. And if we pick Wilcoxon test, let's try that. Okay, Wilcoxon test. You see that? The analysis basically is Wilcoxon / Kruskal-Wallis. So JMP has the same output, right? It says, I'm going to use the same, I'm going to use different techniques. It depends on how many factors, levels it found in the file. So if it finds 2 factor levels, it will do the Wilcoxon test. If it will find 3 or more factor levels, it will do Kruskal-Wallis test. So it dynamically finds how many levels we have in the study and will apply the right test. Okay? So in our case, obviously 1, 2, 3 levels, so it will use Kruskal-Wallis test. Okay? Here's my p-value. Remember we said that from this picture, likely things change over time, right? Strength is not the same. Do I have a confirmation statistically? Yes, I do, right? My p-value right there, it's a chi-squared approximation. My p-value is very small, which means that I have to reject the null in favor of alternative, and my alternative says that over time things change, right, for the concrete. At least 2 populations have different locations. So what I saw in the picture, now I'm getting confirmation from the test. Make sense? So it does matter how old is concrete, because its properties look like they change over time. Alright, so I'm going to close out all these samples. Alright, next question. That was number 6, right? Okay, number 7. Lack of sleep is a serious medical issue. It was linked, among other things, to heart attacks and car accidents. People fall asleep behind the wheel, they crash their cars. It's not good. So, Statistics Canada study asked random sample of Canadian adults to report how much time, how long do they sleep normally, right, in terms of hours. Can we conclude that the average amount of sleep is different for men and women? So obviously the data was separated by the gender, right? Men versus women. So let's go ahead and download the sleep file. Okay. Download the sleep file and open it up. And there it is. Okay. So in sample we have 50 records, 50 men and 50 women. These are weird numbers, right? 5.9. The first guy said, I am sleeping 5.9 hours. Where's 0.9 coming from? It's so precise, right? Well, anyhow, it is what it is, right? We're just analyzing data, okay? Data was given and collected to us by somebody else. We don't know the origin of these figures, okay? All right, so let's go through the same series of steps, right? What data type is being studied, what's the experimental design, and what is the appropriate test. So let's go back to our chart. Is that obvious that I'm comparing 2 populations? It is, right? So compare 2 populations. Data type, interval, right? Central location, what's the design? Samples are independent or matched? Independent, right? Because there should be something in common between first guy and the first gal in the sample, right? Second guy and second girl. Nothing really, right? Just random 50 men and random 50 women. So I have independent samples. And the next question is, are they normal or are they non-normal? I'm guessing, because I'm a sneaky person, this time is going to be non-normal. Because we had normal already, right? Well, let's see. Last time I saw these problems was like a year ago. Okay, men and women, distribution. All right. And what do we see? It looks like women are skewed, right? To the right side. And men are severely skewed to the right side. Okay? So men probably is not normal. Let me go ahead and check the normal quantile plot. Yeah, points kind of wiggle around the central line, so I don't know. Let's apply the fit. So I go to the continuous fit normal, and from this one I'm going to ask for a goodness of fit test, and my suspicion is confirmed, right? Low p-value means I reject null that the data are normal, and I have to say that, yep, that's not coming from a normal distribution. So therefore, coming back to my flow chart, what do I say? Samples are non-normal, right? So therefore, I'm looking at Wilcoxon test, right? It says Wilcoxon ranks some test. JUMP calls it simply Wilcoxon test. Okay? Okay, cool. Well, let's go ahead and formulate a hypothesis, but which one, right? What are we studying? Can we conclude from this data that average amount of sleep is different for men and women? And this is a non-parametric test. So therefore, here it is. My null is going to be that the locations are the same, and the alternative is going to be that the locations are different, right? I'm not asking for men are sleeping less than women or other way around. It's like, are they the same or are they different? So now is the locations of populations, men and women. Men and women are the same. Are the same. And my alternative, just like always, equal, not equal, right? The locations are different. Locations of population, men and women, are different. Okay, that's what I'm testing. All right, so independent samples, what do I do with them? Stack them. Okay, so let's close that one. We don't need that anymore. Stack tables, stack both men and women. So I'm studying sleep amount, right? Sleep hours based on gender. Agree? Gender is the factor of study. The response is how much time do they sleep. Okay, so fit y by x. That's where I go. And my response is sleep hours, and my factor of study is gender. And I click OK. What do you think? Do they look similar? Well, at least on this scatter plot. Pretty similar, right? So let me call for means and standard deviations. Not that they're useful, especially means, right? Okay, so on average, it looks like if I'm using means, 6.56 versus 6.62, fairly close, right? But of course, means are not very meaningful because data is screwed up. It's not normally distributed. So I'm going to use Wilcoxon test, right? So what do? I go to non-parametric, and I use the Wilcoxon test. Let's stay away from exact test, right? We discussed that already today, because probably exact test will hang up on you, right? Because our samples are fairly big. It will take forever. So let's use the approximation for the Wilcoxon test, okay? So there it is. All right, and I'm looking at the probability And again, the output says Wilcoxon or Kruskal-Wallis. It will pick actually Wilcoxon because I have only two levels, males and females, right? It will dynamically pick the right test. Okay, so here is my probability greater than z. If I use normal approximation, and probability greater than chi-squared, if I use chi-squared approximation, they should be fairly close, and they are, right? 0.61 and 0.61. Okay, so what do I do with 0.61? Keep the null or reject the null? Keep the null, right? High p-value, I fail to reject the null, so therefore my null is true, I don't reject that, so my null is true. And what do we conclude? Do men and women have different sleep time statistically? No, not really. Everybody is lacking sleep, right? Just the same, equally. Okay. Do you want to take a break or do you want to keep going? It's up to you. Take a break? Okay, let's take a break. Okay. Oops. Let me put that down. All right. Number 8. Each person hired by Deloitte and Touche, which is a big consulting company, right, takes an aptitude test, which is scored on a scale from 1 to 100. 1 being the highest score, and 1 being the lowest score. 100 being the highest score, and 1 the lowest. After the first year, each employee is going through the performance evaluations, and they're scaled on the scale from 1 to 10, 1 being doesn't meet the minimal requirement, and 10 being highest performance, exemplary performance. Okay, so hiring manager suspects that how well or bad the person does on the aptitude assessment test has little to do with the subsequent performance review, okay, a year later. All right, so let's take a look at the data, and that would be, I don't even know, aptitude test, yeah, this one right there. Aptitude test. All right, so we have 30 people, right? Aptitude test, that's on the scale from 1 to 100, and this is 1 being bad performance, 2 being okay, no, not okay, fair, right, and then acceptable, minimal, acceptable, etc., etc. So different gradations from 1 to 10, okay? All right, so let's go to the flow chart. So what are we dealing with? Look at one population, two populations, compare 3 or more, or is it a relationship? What do you think? I'd say this is a relationship, right? Because your performance on the aptitude test should be related to how well you do a year after, okay? Plus, we can't really compare them directly because you can see one is measured on a scale from 1 to 100, another on a scale from 1 to 10. So comparing the averages or distributions wouldn't make sense because it's apples and oranges, right? We measure it differently, okay? So therefore, I'm starting at comparison, analyzing relationship between two variables. Data type, well, one of them is interval, another is ordinal, right? So we have ordinal, okay? If it's interval and interval, then we have linear correlation, etc., right? But one of them is ordinal, another is interval. So we're talking about Spearman rank correlation test, okay? So what data type being used in the study is a combo of interval and ordinal data. Formulate the hypothesis and test them using the 10% significance. So here is what I'm really testing, okay? We did that actually yesterday in class, right? My null hypothesis is going to be that the Spearman correlation test between the aptitude assessment and the job performance evaluation is equal to 0. Which means that how you perform on the aptitude assessment test has nothing to do with your job evaluation, performance evaluation a year later, okay? And the alternative would be that no, this is a significant relationship, and the coefficient, Spearman coefficient of correlation, it is what it is, it's not 0, okay? All right, so it's actually fairly straightforward to do. That's going to be a fairly short problem. So let's go to the data, and I'm going into the analyze multivariate methods, multivariate, okay, and calculate the correlation between aptitude and 1 year review. So I place them both in Y column, click OK, and here is my correlation. It doesn't look like much actually, right? So if I would treat these variables as interval and interval, that's actually pretty bad, right? Looks like there is a vertical ellipse, more vertically oriented ellipse, okay? So which means that my range for X's, 1 year review, is fairly narrow, but my range for aptitudes is fairly wide, okay? And therefore, for any value of X, you have a wide possible range of aptitude tests, right? So therefore, to me, it looks like for that to be a valid relationship, it should be diagonal, right? If it's horizontal, that means it's flat, it's not affected. If it's vertical, basically means that you have a wide variability in your responses. Also, no correlation. And you can see that from the coefficient of correlation, 0.03. But that's a straight coefficient of correlation, as if my X is interval and my Y is also interval, okay? I don't have that. Instead of that, I have Spearman rank correlation test, right? So let's go into the red triangle menu, and among non-parametric correlations, let's pick up Spearman. That's what we did yesterday in class, right? Kaboom. And what I have is, well, slightly different value, minus 1.588. That's the value of the Spearman rank correlation. But the p-value for this thing is 0.4. Okay, so let me go back. So from the analysis, this one is 0.1588, but the p-value for the test is 0.41 or 40, I don't remember. 40? Okay, 40. And that is higher than 5% or 10% for that matter, right? So therefore, p-value is high, I keep the null, and I don't reject that in favor of alternative, okay? So what does my null tell me? That my Spearman correlation coefficient, even though I see the value 0.15, is that a statistically significant value? No, not really. I can replace it with 0. So it looks like I don't have an evidence to say that this is a statistically significant relationship. So therefore, suspicions of the manager, who is saying that maybe how we evaluate candidates has no influence on their job performance a year later. That is true, actually, right? Based on this analysis. Even the coefficient of correlation is weak, right? But even though it's weak, it doesn't really matter, because my p-value says that essentially what I have is not a correlation at all. They're not related to each other. Sean?
Please restate the hypotheses.
Say again?
Please restate the hypotheses. The R is equal to 0. That interprets into English.
That means that the performance on the annual review is not affected statistically by the aptitude test at the moment of hire. They're not statistically correlated with each other. Okay, that's basically what it says. All right. So therefore, they may want to rethink how they select the candidates. Right. The aptitude test essentially doesn't tell them anything about is it a good employee in the future or is it a bad employee. They may want to redesign the aptitude test, make it more relevant, do something, right? Because right now, pretty much it doesn't tell them anything. Okay, and the last problem that we have in our review set, I believe this is the last one, number 9, is this one. It's very difficult to advertise products geared towards children because children have very short attention span, right? They can't sit in one place. Therefore, commercials for kids goods must be very carefully designed to keep their attention. Okay? Marketing research company would like to investigate whether differences in attention span exist between children watching advertising for different types of products. In the study, they had 4 groups of 50 kids, right? And each group was exposed to different, to the entertaining program. I don't know what it is, like Barney or whatever, right? Clifford the Big Red Dog. There is a conspiracy theory, you know that, about Clifford the Big Red Dog. Why is he so big? Okay, I'll tell you later. My 18-year-old told me conspiracy theory behind Clifford the Big Red Dog. Okay, so each program, though, contained 1 commercial in the middle of broadcasting. And first group, first 50 kids, they saw a commercial for a computer game. Second group, they saw a commercial for cereal breakfast. Third group is clothing. And fourth group, a new toy. Commercials last exactly 60 seconds. But what they measured is attention span, how long they keep watching the commercial, also in seconds. Could be all 60, could be shorter than that, right? So the results are recorded in the file kids commercials, right there. Kids commercials, let's open it up. And what do we see? We see 4 columns of data, right? 4 different groups of 50 kids each. So let's go back to our selection. What am I looking at? Investigate 1 population, compare 2 or more, or is it a relationship? I'm comparing really 4 populations, right? Because measurements are the same. It's seconds, how long does it take them, to keep watching on the screen, right, and then get distracted. So I'm right here, comparing 3 or more populations. Data type interval, agree? Because all these numbers, they're measurements in terms of seconds. So interval data type. Experimental design. Do I have independent samples? Or do I have blocks? Or do I have blocks with replications? What do you think? That goes back how the data was collected, right? They took 4 groups of 50 kids, and each group was exposed to 1 type of commercial. So what do you think? Independent samples, right? What would make this thing to be matched pairs? That would be same kid, different commercial, right? So include 4 commercials in this program, right? And make everybody watch them, right? And measure how much time every kid keeps watching the commercial, right? That would be matched pairs, right? Or blocks. But here, it's completely random sample 1, random sample 2, not related. So that makes them independent. And now all important question, of course, is what's my distribution? If it's normal, then we're talking about one-way ANOVA. If it's non-normal, that would be Kruskal-Wallis, right? Okay, so it looks like I need to test normality. So let's go to distribution, game, cereal, toy, close. All right, well, they're not looking too bad, but let's test them. So game, normal plot, looks fine to you? Normal quantile plot? It's actually pretty good. But if you want to be really formal about that, let's do the continuous feed, normal. And after that, we're going to ask for goodness of fit. I'm looking for high p-value, right? That confirms normality. That one seems to be good and normal. How about game? No, game, we looked at the game, right? So let me go ahead and collapse that. Serial. Now, serial, normal quantile plot. It also looks good, actually. So I'm not going to even test that. Let me collapse this thing. What about clothes? Clothes, I have normal distribution, so that also looks good, right? Almost perfect. And this one, normal quantile plot. Yep, normal distribution. So I have all normal. Well, I was under impression that at least one of them would be non-normal, right? So that we have one-way ANOVA. So that we have Kruskal-Wallis. Did we have Kruskal-Wallis before already in this set? Oh, we did. So this one, yeah, this one is one-way ANOVA. And in one-way ANOVA, I'm testing these hypotheses, right? Just like in Kruskal, I'm going to say that my null is going to be that the average attention span when they watch the game commercial is the same as the average span when they watch the cereal commercial, is the same as clothes, is the same as for the toy, right? So in other words, doesn't matter which product we advertise for kids, they're equally interested or disinterested in the commercial, right? Type of the product doesn't affect the attention span. Or alternatively, I'm going to say at least two products differ in attention span, right? Two products differ in average AVG attention span. Okay? That's what I'm testing with ANOVA. I can use averages because things are looking normal. So let's go ahead and do that. Independent samples, I stack them, right? Tables, stack, game, serial, close, toy, stack, and I'm going to call the data attention span. And the columns are going to be product type, right? Product type. Oops, product type. Okay, so here's my stacked data. And after that, I go to fit y by x. I'm studying the response that would be attention span based on the product type. That would be factor, right? Factor of study is the product type. Click OK, and it gives me this. Ooh, look at that. Well, first of all, let's pull out the means and standard deviations. Okay? So means and standard deviations. Means are, I'm not sure quite honestly, 38, 35, 38, 41. So the range is between 35 to 41. Okay? So I don't know if that will indicate differences or not. Let's see. So I'm going to go to the menu and say means / ANOVA, right? That's what I'm testing. When I click OK, here is my ANOVA output, analysis of variances, okay? And the p-value is 0.026. The only hypothesis that I test, right here, 0.0260. And it's less than 5%, right, p-value. So when the p-value is low, I reject the null in favor of alternative. And what does alternative say? Not all products keep their attention the same way, right? And that probably makes sense, okay? If you would have to guess between these four, games, cereal, clothes, and toys, which one do you think is the least appealing? Clothes, right? Who cares? There is a toy, there's a game, right? Even cereal, pretty boring, but still, it's more probably exciting than clothes, right? So, not all the products are equally exciting for children. So therefore, you have to distinguish and differentiate, right? And that's where ANOVA ends. That's the extent of how far we can go with ANOVA, okay? That's the end of it. All right, any questions? That was last problem for the review, right? Any questions, concerns, complaints, sarcastic comments? Anything unclear, hazy, shady, weird, awkward, plain out of sync with evolution? All right, so I'm going to stop. Sure, go ahead.
So for the comparative theory and moral population part, I'm curious about the experimental design is independent and then blocks and what is
With replications, yeah. With replications, basically, let's go back to our file, right? We didn't study with replications. But here's what it is. In my case, I don't have blocks because that kid is different from that kid, is different from that kid, is different from that kid, right? That makes them independent. We just discussed what will make them matched is if I put all commercials in the same program and make 50 kids watch it, right? In this case, I'm measuring attention span for the game, cereal, clothes, and toy for the same kid, right? So if they are like hyperactive or they are on the other end of spectrum, that will be reflected, right? How long it keeps their attention. That would be blocks with no replications because each kid watches the commercial only once, right? Replicating would be, for me, for example, to take, the same kid and include the same commercial. Like, for example, let's say I have a program, right? Barney or something. So I put these 4 commercials in the Barney program and make them watch this Barney program, and I measure for one kid how long they watch that game, cereal, clothes, and toys, right? Then I do another educational program like Thomas the Train or something, or Clifford the Big Red Dog, and I include the same commercials again. So they watch the program, but they're exposed to the same commercial, and I do the same measurements again. So for each kid, I have several numbers, right? How long did they watch the commercial for the game? Number 1, number 2, number 3, number 4, right? 4 times they watched this commercial. That would be, I'm replicating for the same kid and for the same commercial, I'm getting more than one observation. That would be creating replicas, okay? But we didn't study that, so therefore I'm kind of skipping that altogether, okay? All right.